Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about organic photochemistry. So I will discuss about on the following title: Introductions to Photochemistry, Classification of Photochemical Reactions, and Application of Photochemistry in Organic Synthesis. So, what is photochemistry? Chemical reaction initiated by light. Energy is absorbed or emitted by matter in discrete quanta called photon. You all know E is equal to h nu, which is equal to Sc by lambda. Short lambda light correspond to high energy. Absorption of light lead to an electronic excitation, ground state to excited state. Promotion and electrons like an N to pi star transition or pi to pi star transition. Most chemistry takes place from S1 and T1 excited state. S1 have a shorter lifetime and higher energy, and T1 has longer lifetime because spin flip required. So energies, 100 kilocalorie per mole is equal to 4.3 electron volt, which is equal to 286 nanometer, which is equal to 35,000 per centimeter near UV nano. So 286 kilocalorie per mole is equal to 12.4 electron volt is equal to 100 nanometer, and it is a far UV. So typical bond energy CH 110 kilocalorie per mole, carbon-carbon 80 kilocalorie per mole, carbon-carbon double bond 150 kilocalorie per mole, and so on. Now you can see the potential energy V0, V1, V2, V3. This is the A, E1 and E2 energy level. So chemically useful light is generally in the range of 200 to 400 nanometer, often employ filter to regulate the wavelength of the radiation. Ground state is 0. You can see here N to pi star S1, N to pi star T1, and pi to pi star transition, and S1 and pi to pi star T1. So a Jablonski diagram named after Polish physicist Jablonski is a diagram that illustrates the electronic state of a molecule and transition between them. The states are arranged vertically by energy and grouped horizontally by spin multiplicity. Radiate transitions are indicated by straight arrows and non-radiative transition by squiggly arrow. The vibrational ground state of each electronic state are indicated with thick lines and higher rotational state with the thinner line. So you can see here the Jablonski diagram from S0, then you can see the IC interconversions, intersystem crossing, internal crossing, and T1 state. This diagram is Jablonski diagram. So physical process undergone by excited molecules: S0 H nu S1 excitation, S1V S1 heat vibrational relaxation, S1 to S0 H nu fluorescence, S1 to S0 heat internal conversion, S1 to T1 intersystem crossing, T1V to T1 plus heat vibrational relaxations, T1V to S0 plus H nu phosphorescence, T1 to S0 plus heat intersystem crossing, S1 AS0 S0 AS1 singlet energy transfer, T1 AS0 S0 AT1 triplet energy transfer. So why use photochemistry? Overcome large kinetic barrier in a short amount of time, produce immense molecular complexity in single step, form thermodynamically disfavored product, allow reactivity that would otherwise be inaccessible almost any other synthetic method. The reagent light is cheap, easily accessible, and renewable. What is the drawback? Reactivity is often unpredictable. Many substrates are not compatible. Selectivity and conversions are sometimes low. Chemical process undergone by excited molecules. A, B, C give AB radicals and C radicals simple cleavage. A, B, C give the E plus F decomposition. A, B, C give ACB intramolecular rearrangement. ABC give ABC prime photoisomerization. ABC RH give ABC H R radical hydrogen atom abstraction. ABC give ABC2 photodimerization. ABCA ABCA star photosensitization. So friends, alpha cleavage, this is Nordish type 1 reaction. In solution, the radical undergo further reaction to give products. So these reactions I am going to show you here. So this reaction is known as Nordish type 1 reaction. Here alpha cleavage, you can see carbon and carbon bond break and forming radicals, and further it gives the products. So here you can see in the second example, carbon bond break and radical formation occurs, and then remove the CO and forming 4-member ring. So hydrogen abstraction followed by cleavage, Nordish type 2 cleavage. The radical can abstract a hydrogen atom from a donor. The resulting radical can then undergo further reactions. So you can see this reaction have the 3 products, 2 product 90%, 1 only 10%. So what is the mechanism here? You can see the abstraction of hydrogen from gamma, and there is a formation of 4-member ring, and then further cleavage it gave the enol and alkene, and enol further converted into ketone. This is happened due to keto-enol tautomerism. So an intramolecular examples also available. You can see the abstraction and forming the products. So abstraction of hydrogen from 5th position, forming the cyclic products, and then you can see the final product. So geometrical isomerism, you know, cis-2 trans conversion, cis-2 trans conversion undergo photochemical condition, commonly lead to thermodynamically less stable isomers. Cis isomer typically absorb at lower wavelength due to decreased conjugate because of non-bonded interaction. Reaction come to photostationary state unless optical pumping is performed, irradiation of just one isomer to drive the equilibrium. Now dipymethane rearrangement. Zimmermann has studied this reaction extensively. Reaction takes 1,4-diene or 3-phenyl alkenes to phenyl or phenyl cyclopropane. You can see the formations of diradicals, which is further rearranged and forming another diradical, and finally formation of the product. So baryenes, this is baryenes, you can see, and formation of semi-bulvalines, and the another products you can see the formations of tricycle ring. Oxidipymethane rearrangement. In place of double bond you have the oxygen also, and the same way 3-member ring form. If you have this substrate, then you can see the product in presence of Pyrex T-butanol 50%, and then you have the reactant like this acetone, it gave this type of product. So HNU 300 nanometer solvent, it gave the many products,